All right.
Anyway, thanks very much. I'm delighted to be back for another conference, and congratulations to the Bayesian crew for 10 years of successful meetings. Certainly, back in the day, I had red hair. Stefan had no gray hair. Lionel still had no hair. So some things change and some things stay the same. But what I'm presenting on today is some initial thinking that I've been doing around the application of causal analysis to the challenge of understanding cumulative environmental impacts. So yeah, we're staying on this environmental theme, which is pretty fun to see. And yeah, following me is John Gerger, and he helped me with some initial thinking around this piece because this is very much the kind of world that he lives in. And this particular photo is of the construction of the so-called Site C Dam on the Peace River in northern British Columbia, and at a cost of over 16 billion Canadian dollars. It's the most expensive public infrastructure project ever undertaken in the province, and it's been very controversial because of its cost, because of the environmental damage that will be caused when the valley is eventually flooded, and as well as plenty of opposition from local farmers, local Indigenous people. It's been a very difficult project. However, we've been talking about climate change. It's going to generate enough carbon-free electricity to power 500,000 homes for at least 100 years. So, as the economist Thomas Sowell said, there are no solutions, just trade-offs. It's one of the challenges that we faced, obviously, in a changing world, which is something we've been talking about already this morning. When I talk about cumulative environmental impacts, I want to start with a bit of a definition. It's a very straightforward definition. Changes to the environment that are caused by an action in combination with other past, present, and future actions. And this is a kind of a very rudimentary kind of way of looking at things, but this is generally how things are viewed in the cumulative effects world. And the point here, of course, is that significant environmental degradation is rarely the result of a single acute event, but is more often caused by the additive and or synergistic effects of several different stressors. So a good example here, here's another photo of an area nearby where that dam is being constructed. And you can see some of the cumulative effects of the things that have been happening on this landscape. These are all forestry cut blocks in here, these light colors, and then all these dots are actually gas wells, natural gas wells, all connected by roads and pipelines. So in some of these areas, you can get quite an intensity of things sitting on top of each other. And of course, if you just look at one particular cut block or just one particular well, it doesn't have much of an impact, but these things tend to add up over time. So assessing these cumulative impacts is an important component of environmental assessments, which are usually conducted when there's a big project like that dam is proposed. What they want to do is make sure they take into consideration all the things that have already happened on that landscape, as well as what we would call future foreseeable impacts, which are things that are going to happen on the land base that are planned but haven't occurred yet. But the definitions and procedures for this are theoretically weak, and it just basically works on a bit of what I would just call a bucket approach. And so with respect to whatever environmental value that we're talking about, as I said, there's some assessment of the current condition, some assessment of what will happen when you add the project to the mix, and then what happens if there's some sort of future foreseeable impact that's planned. And if you have the project impact, which pushes it over some sort of impact threshold, then that's considered to be a significant project effect. If that doesn't get you there, but the future impact pushes you over that threshold, then they talk about that as a significant cumulative impact. But there's many problems like this, and notwithstanding what Edwin was just talking about around threshold effects and moving into different states, threshold effects are actually fairly rarely identified in big ecological systems. Edwin's system is actually fairly simple because he's adding a few species and adding a few things and looking for those tipping points. It's generally much easier to find in a system like that. But if you think of ecosystems, broad scale, continent-wide ecosystems that have many interacting factors, feedbacks, and time lags, and those things tend to attenuate the responses and make these thresholds very difficult to find. The other thing that this pushes us towards is a very simple relationship between stressor and outcome. It's generally assumed to be directly causal and deterministic. You push it over that threshold and you're done. And the third thing is that when we think about the importance of counterfactuals, what would happen if the project were not conducted? This kind of model keeps things fairly simple. It doesn't take into account some other things that might be going on. So maybe the project doesn't push things over the threshold, but even if you didn't do the project, maybe there'd be some other stressor that might. So, and we've been talking about climate change, which of course is the classic one we've been discussing already this morning quite a bit. And so that's where causal analysis comes in, and many on the call, maybe not all of you, depending on your particular work around Bayesian networks, but obviously there's a natural fit between causal analysis and Bayesian networks because causal graphs can be represented as probabilistic Bayesian networks. But of course, not all causal models are Bayesian networks, and not all Bayesian networks are causal models, but there's an intersection between those two if the graphs meet certain criteria. So BayesiaLab, of course, has tools and procedures for supporting causal analysis, and you can always read chapter 10 of the textbook for an excellent introduction on that and the tools that are available. And this is a quick example of a causal model for the caribou system in Western Canada that I've spent much of my time thinking about and which I've, of course, presented on during several past conferences. And the question is, how could causal analysis help? And I think there's a few things in which we could make some gains here. So we could first provide a theoretical framework, theoretical and mathematical framework for actually estimating the types of cumulative effects that may be happening. And I think that's a good calculus around that. I think it's fairly rare at the moment. And also there's obviously all the usual benefits of these kinds of models that they help make our assumptions very transparent. And they shift us from this deterministic to a probabilistic perspective, which I think is very useful when we're talking about these big uncertain systems, and a broader consideration of those counterfactuals more explicitly. So I think that's important. So let's focus on those counterfactuals for a moment and talk about whenever we're trying to assess the impact on some value, some wide-ranging value, where we don't necessarily have experimental evidence. Of course, we're trying to understand what the impact of things that are happening on caribou is. We have to base our future predictions on events that have happened in the past. Those events might have been under management control. Perhaps there was a permit issued for a gas well. But of course, there's lots of events that happen that aren't necessarily under our control. So they're not really part of an experiment. We're always faced with this problem. How do we know that the observed event was caused by the outcome that we're concerned about? And that requires this comparison to the counterfactual. What would have happened had the event, what would the outcome had been if the event, what would the outcome have been had the event not happened? I have to apologize to anybody who's not on the call, whose first language is not English, because the language around this gets fairly tortured in the use of tenses. And as you know, in English, we have a lot of different ways of explaining what might, could, and had happened in the past. So I know it gets a little confusing. So apologies for that, but I'll try to step through this. So kind of the toy example we always use around this is, well, I took an aspirin and my headache went away. Would it have gone away if I had not taken the aspirin? If you read any of Pearl's books, you'll see that example all over the place. And we can use causal models to help us infer the outcomes of speculative past and futures. And we can do that in the absence of experimental evidence, as long as we have a causal model that meets a couple of criteria. And so if it's exogenous, so that it's not confounded, your treatment isn't confounded, and we assume this monotonic relationship. So if you take an aspirin, the only thing it can do is make the headache go away. It can't produce a headache. That's monotonicity. And so we have this now structure, causal modeling, for using our observational evidence to speculate about future what led to the current conditions from the past and how things might change in the future. And this is where I want to talk a little bit about the concepts of necessary and sufficient causation. I think that this is, Pearl presents this as part of rung 3 of his ladder of causation. It's talked about in the books. We don't hear much about it in the broader literature, but I think it's a concept that we should be speaking about more often, because I think it makes a good, I think it is currently underutilized a bit. And so if we step through what we mean by this, necessary causation is, just as I said with the aspirin example that I just talked about, probability that the outcome would not have occurred in the absence of the event, given that they both did occur. So back to our toy example, what's the probability that my headache wouldn't have gone away if I hadn't taken the aspirin, given that I did take the aspirin and my headache did go away? And then sufficient causation is on the other side of that, which is, okay, my headache didn't go away, but I didn't take the aspirin. What's the probability that it would have gone away had I taken the aspirin? Two sides of sort of the same coin. But of course, then we can put those together and talk about sufficient and necessary causation, probability that the outcome would have occurred in the presence of the event and would not have occurred in its absence. And I think pulling this back into the context of cumulative effects, I think that this definition comes closest to what it is that we're trying to figure out. We need an estimate of the probability that some adverse outcome will happen if the project occurs, and it will not happen if the project doesn't go ahead. And so that's what we're trying to tease apart here. Okay, sorry, maybe I missed that last line. Now, the good thing is, if we just talk about, let's keep our examples really simple. This is some initial thinking. I'm still trying to work through this using kind of the simplest examples that I can come up with. And so if we start with the position that our treatment is exogenous, we have this very, very simple treatment causes outcome causal model, then the math to estimate these different types of causation is really trivial. And so we have our calculation of the factual, the probability that we did that we do get the outcome given that the treatment was imposed, as opposed to the counterfactual, which is the probability that the treatment occurs given that the outcome occurs given that the treatment was not imposed. And then very, very simple calculations to come up with your various probabilities. And so to apply this in kind of a couple of the simplest situations that I can think of, the first one, and I've talked about this particular system before, this is caribou in northern Canada, concerned about habitat impacts. And there's this great deal of concern about the relationship between anthropogenic disturbance and wildfire on caribou demographics. That's what's being presented here in the graph in the bottom right-hand corner. Habitat disturbance is a percentage of the land base along the x-axis. The y-axis is what we call recruitment, which is basically the number of baby caribou that are quote recruited into the adult population, become part of the breeding population. And you can see that there's this definite trend towards this lower recruitment as habitat disturbance increases. These locations are weighted by observations. That's why the bubbles are different sizes. But there's a lot of scatter around that. And there's a policy threshold. Like we said, there's that policy threshold that we want to stay under. And that policy threshold is currently 35% undisturbed habitat. And that's what I've represented here as this vertical line. So generally, we want to manage to a condition where the habitat disturbance is less than 35%. And as you get over 35%, you can see that we end up with the situation where we have caribou in a lot worse condition. And then this horizontal line basically is the estimate of the point above which caribou are doing fine, below which they're not doing fine. And we can just tally up the weighted dots in there to come up with a table and see how it falls out depending on whether the treatment was imposed and then what the outcome was. And then doing that, we can very quickly run the numbers, and we run out the probability, necessity, sufficiency, and both. And so we quickly come to the conclusion that there's only actually a 30% probability that the disturbance, that habitat disturbance, was necessary to cause those population declines, but a higher sufficient causation, 57%, to cause the population decline, and a 24% probability that the disturbance was both necessary and sufficient. So I think the most interesting thing here is the probability of the low probability of necessary causation. And I think that is happening here because certainly while higher disturbance was correlated with lower recruitment, many of the ranges that had low disturbance were still also in decline. So in that case, we can't look to disturbance as a cause necessarily, because there must have been some other things going on there. So the necessary causation is relatively low. And the probability of sufficient causation is higher because most of the highly disturbed ranges were in decline, 75 out of 92 here, or 92. And so I think that this actually sets us up in a much stronger way than if we're just looking at that single relationship. So this suggests to me that in areas where we have caribou already decline in highly disturbed areas, if we try to address that through something like restoration, it's probably not going to be that successful. But at the same time, if we have caribou that are in good shape, where we have low disturbance, chances are we should probably do what we can to avoid adding additional disturbance onto those areas. So this is one super simple example. The other super simple example that I want to talk about is when we don't necessarily have this kind of data, but we can still use a causal approach to kind of reason through some of these things. And so for this, I'm going to turn to the topic of grizzly bears. I guess I should have put a grizzly bear video in. That's what I should have done. But so this grizzly bear, by the way, his name is Spanky, and I had the privilege of meeting him on the Kutsumateen River many years ago now, before we had cell phones, so phone cameras. So I guess that's why I don't have the video of him, just a picture. I assisted on a research project. This is an estuary of a river that flows into the Pacific Ocean just south of the Alaska Panhandle. And grizzly bears are obviously an iconic species in North America. Most of the population is in British Columbia, Yukon, Alaska. And it's a very important consideration in most environmental impact assessments. One of the main indicators we use to assess impacts on grizzly bears in development projects is road density. And based on some literature that goes back about 25 years now, the relationship is, again, treated in a very simple way. So we have this cause of road density, and this result being higher rates of grizzly bear mortality. And the threshold that's applied to this is a threshold density of roads of 0.6 kilometers per square kilometer. And under this particular model, we're under this kind of deterministic model as it's expressed here, we have this, the probability of necessity and the probability of sufficiency are essentially one. They're essentially unity. So if you want to have more bears, basically fewer roads. However, to riff on a somewhat commonly heard phrase, roads don't kill bears, people kill bears. And later research points to a slightly more complex model, which is that, of course, because roads don't kill bears, the real thing that you're trying to avoid, of course, are these human bear encounters, and that requires a population density. There's got to be some people. If you got roads, you got no people on them. It doesn't really, those roads don't necessarily have an effect. And I know that seems obvious, but it's kind of remarkable how much we just get tied into these very simple indicators, and you trip that indicator and everybody goes out and says, oh, well, obviously the mitigation you got to do is to restore those roads if you want the project to go ahead. And the question is that the most efficient way of doing it? So under this model, of course, the real issue here is human bear encounters. A descendant of that is the grizzly bear mortality rate. And this human population density is actually a confounder, because not only does it generate the human bear encounters, because people have to be around, also in places where you have more people, you also have a lot more roads. So there's a bit of a backdoor path here when we're trying to isolate this effect of road density on grizzly bear mortality. And it also suggests a mitigation, and this paper speaks to that mitigation, is that you can put some sort of access management in place, and that basically controls the people on there, and that reduces those human bear encounters. So we can block that backdoor path if we intervene on road density. We can see from here that it's still still a very simple system, but what we've done is we've moved from this very kind of deterministic cause effect to something that is that we can express more probabilistically and with these additional variables and with these covariates. And so when we think about it from the perspective, again, of necessary and sufficient causation, we've moved from this place of where both of those were close to unity in that very simple case to this kind of altered calculus where roads are certainly a necessary cause of mortality, but not sufficient because that requires the presence of people, which we can then mitigate through some sort of access management. So when I start to think about this and just putting this together in my mind on how these pieces could work from the perspective using these very kind of small toy examples, I could scale this up and start to think about how we think about necessary and sufficient causation in these problems. I might start to set it up as a bit of a table where we have low or high necessary causation and low and high sufficient causation. And so maybe in the easiest situation to imagine is where we have both low necessary and low sufficient causation. In this case, the activity should probably be allowed because it's unlikely to trigger some desired outcome. Conversely, if we have high necessary and high sufficient causation, this suggests that there's few ways to avoid that undesired outcome other than just simply preventing that activity. And then, but the other two situations are a little bit different, where one is high and the other is low. So perhaps the activity can proceed, but with some kind of mitigation that depends on which type of causation is more predominant. So in the case of having a high necessary causation, but low sufficient causation, perhaps we can mitigate that effect. So for instance, this goes back to the grizzly bear example, where roads are necessary to drive that unsustainable grizzly bear mortality, but aren't sufficient in the absence of people. So taking actions to control the human element can mitigate that causal effect. The opposite to that, down here where we have low necessary and high sufficient causation, that's what the caribou example was pointing to, although in neither case were they were particularly high. I find this one a little bit more difficult to conceptualize, but I think what it means is that the project can certainly trigger the undesired outcome, but preventing the activity won't necessarily prevent the undesired outcome. So in this case, we have to essentially address multiple pathways if we're going to try to stay below that particular, if we want to prevent that outcome from occurring. So like I said, still very much a work in progress, and I'm still working my way through that. But I think that's where I'm going to stop at this point. And just thank you for your attention and interest. My contact information is there if you'd like to connect on this or anything else. And I realized how many times I said outcome today, and I'm very aware of my crazy Canadian accent, so I apologize for that too. Oh, and I apologize too. So another sign of being Canadian. But thanks very much.